So hello everyone, we are starting now. So this session is PS13, Computer Vision and Machine Learning for XR2 Scene Understanding. So I hope we have an exciting moment here. We have 4 presentations in total. The first one is from TVCZ invited talk, and the other 3 are from conference track, and actually the third one is nominated as one of the best paper nominees. So, yeah. So let's start. The first presentation is about CRefNet, learning consistent reflectance estimation with a decoder-sharing transformers, presented by Jundan. So please go ahead.
Thank you for the introduction. Hello everyone, I'm Jundan, a PhD student at the University of Bath. I'm happy today to share our work, CRefNet, learning consistent reflectance estimation with a decoder-sharing transformer. Let's start with a simple explanation of intrinsic image decomposition. An object's appearance comes from different physical properties working together. Intrinsic image decomposition is the process of identifying these properties from a single input. In our work, we assume the scene is pure Gaussian and decompose it into 2 parts. A reflectance image multiplied by a shading image. The reflectance shows the object's color and texture, while the shading shows the geometry and lighting effects. Separating these layers is useful for editing images realistically. Importantly, getting the reflectance is essential when we want to maintain the original textures in the scene. However, achieving perceptually consistent reflectance remains a challenge. Reflectance consistency means all pixels of the same material should have the same reflectance color. There are a few reasons why this is difficult. First, pixels of the same material may be distant. For example, a large wall in this image has the same material. This previous convolutional model struggles to assign a same color, while our model can achieve global consistency. Another challenge is the changing appearance of materials due to varying lighting conditions. Shadows, highlights, and sometimes over or under exposure can significantly affect a material's appearance in the final photo. Usually, the greater the lighting variation, the harder it is to accurately estimate reflectance. For example, in this image, it's hard to recognize that all these regions have the same reflectance, but our model can successfully identify them. Inspired by how humans judge reflectance in the IW benchmark, we believe it's important to establish relationships between regions with the same or different materials. Here's an example. In this image, we can see that some surfaces and objects share similar white or grayscale appearances, like the fridge, door, wardrobe, dishwasher, and the window frame. On the other hand, the tiles and the floor appear darker. To predict the relative brightness of all materials in this scene, it's helpful to model long-distance dependencies. For this reason, we introduced transformers in our work and propose a new decoder-sharing training strategy to enhance the quality. Let's take a look at our CRefNet approach. We've conducted experiments on both reflectance and shading estimation, but we'll focus on reflectance here. Our training process consists of 2 branches. First, we have the reflectance estimation. We input an image and generate its reflectance. Second, we have reflectance reconstruction. Both the input and the output are reflectance. These 2 branches share a reflectance decoder, allowing the estimation branch to learn from the knowledge in the reconstruction branch. Let's go to the estimation branch first. The main ideal in the estimation branch is to enable effective long-range information exchange. To achieve this, we introduce a transformer module. This module works with image features extracted by a convolutional encoder. Compared with the input, the image embedding space has a lower spatial resolution. This helps our transformer module to look at the entire image and translates the features from image embedding to reflectance embedding, which are then decoded by a convolutional decoder. The key component is the swing V2 transformer module at the bottleneck. Transformers use self-attention to capture long-range relationships. We choose swing V2 because it reduces computational complexity compared to a standard transformer. We experimented with replacing the transformer with 22 residual blocks, which have a similar number of trainable parameters. This change results in a significant decrease in global consistency. Please look at the ceilings in these images. The residual blocks produce substantial color variations, while the transformers do much better. Overall, transformers are ideally suited for achieving consistency. Now that we have the reflectance estimation branch, we propose to train it jointly with an auxiliary branch, the reflectance reconstruction. The main purpose of this auxiliary branch is to regularize the reflectance embedding space. It works like an autoencoder. The encoder takes the input reflectance and transforms it into an embedding. Then the decoder reconstructs it back. Both branches share the same decoder, so they share the same hidden embedding space. Note that at inference time, the reconstruction branch is not needed. Autoencoding is commonly applied in image generation to ensure that generated images follow a specific data distribution. In our project, we observed a similar effect. Without the reconstruction task, the estimated reflectance has more lighting effects, such as highlights and specular reflections. Using the reconstruction task, the estimated reflectance looks more Lambertian. This means there are fewer extreme lighting effects, and the reflectance looks smoother and more consistent with its surroundings. In conclusion, the reflectance reconstruction task helps regularize the output, ensuring it follows more desirable reflectance patterns. Both the estimated and the reconstructed reflectance are supervised using dense ground truth from synthetic data. Our dense supervision captures errors in the image domain and the gradient domain. This is the multi-scale gradient loss we adopt. Here we calculate errors between our predictions and the ground truth in both the x and y directions of the gradient maps. We compute these errors at 4 different scales, allowing pixels to interact with distant ones, not just their neighbors. Based on this, we introduce a rectified gradient filter, which suppresses minor changes in the ground truth reflectance. It works similarly to a two-sided ReLU activation, so we call it a rectified gradient filter. If the gradient falls below a certain threshold, we reduce it to 0. This helps reduce ambiguities caused by small changes in the appearance of the input. As a result, we observe better local consistency in the reflectance after using the rectified gradient filter. It is designed to smooth reflectance maps. It helps the model remove shadows on surfaces and eliminates unwanted high-frequency shading details. Furthermore, the RGF is a powerful and efficient method for image flattening in supervised learning. It requires only a small change to the gradient loss and adds no actual computational cost during inference. As a result, at the time we submitted this paper, our model achieved state-of-the-art performance in reflectance estimation based on perceptual metrics. It showed competitive performance in shading estimation. Besides, it also achieved the best performance on the MIT intrinsic benchmark using dense metrics. For more experimental results and detailed explanations, please refer to our paper. Let's look at some visual comparisons with other related works. Our reflectance estimation is more robust, especially in areas with colorful lighting. Take this wall, for example. Because of the colorful lighting and inter-reflection, the upper part of the wall appears slightly yellow, while the lower part seems somewhat blue. The ordinal shading method cannot predict a consistent color for the entire wall. By contrast, our model predicts a more uniform color. In dark regions, there's some input noise due to the low dynamic range and the low quality of the image. Our model is less sensitive to this noise, which helps produce a cleaner result with fewer artifacts. Besides, our model performs well in predicting consistent reflectance across large areas. As shown, even when there are very bright lights or overexposed regions in the image, our model can handle it. Our model can also handle shiny surfaces. It removes the specular reflections on the floor. Specular surfaces are especially difficult in intrinsic image composition because they look quite different depending on the intensity of the reflections. Since we submitted our work, several diffusion-based intrinsic image models have been introduced. One challenge with diffusion models is handling irregular patterns like text. For example, in this case, the intrinsic diffusion model struggles to completely remove shadows from the reflectance layer. And it produces letters that look similar to the input at first glance, but when we look closely, they are not the same. The same issue with text on the poster. The text generated by this diffusion model looks blurry and some parts are difficult to recognize. This shows the key challenge with diffusion-based models. It's hard to ensure the generative textures match the original input. In contrast, long diffusion models like ours handle this much better. Furthermore, I would like to highlight the significant computational gap. The intrinsic diffusion model requires 8 A100, running for 65 hours for training. Its inference speed is less than 0.3 FPS. In contrast, our model trains on just 1 3090 for 48 hours, with an inference speed 20 times faster, reaching 7 FPS. This makes our model much more practical for time-sensitive applications. We have made the code available on GitHub. Here are the link and my email address. Feel free to contact me if you have any questions or would like to discuss anything further. Thank you all for your time and interest in our work.
So is there any questions from the floor? Okay, maybe I can start. So from a novice viewpoint, I mean, I'm not familiar with this kind of method, but from a novice point of view, the end result somehow looks quite similar to semantic segmentation results. So within, how can I say, uniform areas and some clear edges. So do you have any ideas on, let's say, taking some insights from those different areas into your work?
Thank you. This is a good question. Actually, this task really looks similar to semantic segmentation somehow. Usually, some baseline models are taken from the semantic segmentation methods, just like the unit. Unit is also a popular one in our task. The main difference is for semantic segmentation, we would like to predict the label for each region, but for this task, it's a regression task, so it's not classification. That means for each pixel, it should have a value. It's not a label in a range or something, but it's an absolute value, a metric value. So this is the main difference. Between the semantic segmentation and indeed there is some joint learning models that takes knowledge or training data from semantic segmentation. It's really, there are some existing methods, and actually I also consider this. But for myself, I would prefer to do something further, like maybe better for material segmentation rather than semantic segmentation. Thank you.
Okay, thank you. So, any questions from the floor? We can have actually plenty of time to have questions. So, meanwhile, I can just have some more questions. Since this is ISMAR, and then I was just curious, how you can, if you have any AR-specific applications in mind by using your methods.
Actually, I didn't show any applications here, but actually it really related to image editing in the AR. Just for example, some popular applications like relighting. If we want to relighting, we want to preserve the color of the material, but only change the lighting. So relighting is a popular application, and somehow there are also some applications like material manipulation. For example, you want to change a Lambertian object into specular or shiny, then you can do some modification on the reflectance layer. These are two more image editing, and there are also some other applications like material transfer. For example, you have one image with some specific materials, and then you want to transfer its color to another scene. It's just like some decoration of the AR scene. So it's material transfer or color transfer like that.
Do you think it's easy to apply your 2D methods to the 3D scenes?
Not such easy, but it's applicable, and there are some. If we consider it into a neural network view, it can do. Sometimes some model can automatically do it. Just like the diffusion model. Like right now, there are some methods they use the conditional generative model, use the reflectance layer as a conditional representation, and then generate some images based on the estimated reflectance. This is some applications. So it's possible.
Cool. Yeah. Cool. So actually, I have another question. So when I looked into the network architecture you had, like 2 lines, the main branch and the second branch, like this one.
Yeah.
And then I thought it's a kind of good idea, as you did, like the sharing the reflectance decoder. But where did you get that inspirations? Like how did you come up with this specific architecture of the network, like 2 lines and then sharing only the decoder?
Sorry, do you mean the inspiration of this architecture?
Yeah, exactly.
Actually, the inspiration comes from the auto-encoding. Yes, yeah. Just at that time, just when we design this model, the transformer is a bit heavy. So we want to make it lighter, not such heavy. So we read some papers in the generative models. And auto-encoding is a technique in generative model to use a relatively smaller latent space, but to generate high quality, high resolution images. So then I realized this auto-encoding may be helpful to help our model to generate reflectance in a desired data distribution. So we try this joint learning. So that means the generative models embarrass me.
Okay, yeah, sounds cool idea.
Thank you.
So any questions from the floor? Okay, so then maybe we can move on to the next presentation. Thanks to the speaker again. So I apologize that I haven't introduced myself at the beginning of this session. I've just noticed that now. My name is Shohei Mori from University of Stuttgart. And yeah, so the next presentation is about multimodal 3D fusion and in-situ learning for spatially aware AI. Presented by Chengyuan.
Okay, good afternoon. My name is Chengyuan, and with my colleagues Radha, Noah, Kangyou, and Professor Höllerer from 4Eyes Lab at UC Santa Barbara, we present multimodal 3D fusion and in-situ machine learning to bring our interpretation of spatially aware AI to augmented reality. Okay, so AR systems have long aimed to seamlessly integrate the virtual and the physical environments. To achieve that, the system needs to understand the user space from the physical boundaries to the where and what of the objects. So users also need the authoring capabilities so that they can improve, okay? and so that they can improve the utility of the virtual content, such as placing virtual objects reasonably and attaching information to physical objects. So with improved context awareness, researchers demonstrated various object-level interaction with physical objects. However, they're often constrained to predefined objects and models. So in recent years, the computer vision community have made leaps in deep learning-based vision language understanding to enhance the environment perception for autonomous tasks. Just a few weeks ago at ECCV, Google researchers showed that how they can reconstruct the entire city of San Francisco and curate the city with natural language questions. So through this work, we also aim to bring this gap between CV and AR to bring spatially aware AI and enable new tools and interfaces for users to interact with the physical spaces and objects. So the contribution in this work are divided into 3 parts. We first present a fast 3D reconstruction pipeline called Multimodal 3D Fusion. This method integrates the geometric, semantic, and vision language knowledge into a unified 3D representation. And then we propose a concept of in-situ machine learning that learns from the user's interaction with the environment for real-time AR applications. And finally, we built a fully functional demo on Magic Leap 2 and a GPU-accelerated system to demonstrate the potential of the system and proposed methods. So here's our proposed workflow. Users can capture the physical space with regular RGBD devices like iPhones or the Magic Leap 2 headsets. And in less than 2 minutes, our pipeline reconstructs the 3D model of this office, and it parses and identifies individual objects without any user annotation or input. And because we're fusing the vision language features into every object voxel and vertices, we're also creating intelligent virtual twins for each physical object. So we'll demonstrate our take on the spatially aware AI through 2 applications. The first one is spatial search with natural language. This allows 3D model to respond to the user's questions, natural language open questions, through a heat map in the asset. And next, what do we mean by intelligent object inventory? So powered by in-situ machine learning, so every user editing to the virtual content, for example, they can mark objects as important, or they can rename the object to give them meaning for higher utility, and they can also merge multiple broken mesh pieces into a single object. All of these user editings are learned by a neural network. And in the future scans, when the future scan of this space is available, the neural network tries to remember and re-identify these previous seen objects. In that case, for example, we can travel back in time to reveal what has been the same and what has been changed. So next, I'd like to provide a little bit detail of the heart of our system. Which is a TSDF-based 3D reconstruction pipeline. It reconstructs the geometrics of the scene. So, but the conventional TSDF doesn't provide any semantic information like the what and where of the objects. So in this work, we extend the TSDF fusion algorithm to build a multimodal scene volume, which fuses the clip model's vision language embeddings into every voxel and vertex of the scene. So in case you're not familiar with CLIP, so it's a neural network that makes a connection between the images and the text of the same meaning by mapping them into the same latent space. So this integration allows us to curate the physical space with abstract or arbitrary natural language questions. So next let's see some real-world demo through the lenses of Magic Leap 2. So here I'm typing things that might be dangerous to babies, because my daughter was born last year, and we were working on this project last year. And this is a real-time recording. In just seconds, our model highlights the rolling chair, objects on the shelf, and there are power plugs on the wall, and there's a basketball on the skateboard, very terrible idea, and also like things on the shelf that could be false. So this is the model responding to this open question. And I just want to mention that by now, we're only utilizing two of the three modalities, the geometrics and the vision language knowledge. But we can unlock new interfaces and interactions by combining these knowledge with object level understanding and in-situ machine learning. So we push our reconstruction pipeline a bit further to integrate the segmentation information to create 3D object level multimodal understanding. So now that we not only know we not only have the vision language features in every voxel and vertex, we also know which group of voxels or vertices belong to which object. So with this object level multimodal understanding, user can directly interact with individual objects in their surrounding and train a spatially aware AI model for downstream tasks. So one practical task is to learn to remember and re-identify individual objects across different scans of the same space. So this can be treated as a 3D object detection or classification problem, which can be very computationally expensive. So in this work, one other thing we did is when we sample the object data for training, we convert the object's volume representation to a graph representation, turning a pretty hard 3D object detection problem into an easier graph classification problem that is more suitable for real-time AR application. So in order for user to guide the training of personalized AI for their physical space, we propose the concept of in-situ machine learning. In-situ is Latin for the meaning of in position or on-site. So the in-situ nature of the object recognition task comes from its training data, ground truth, and evaluation. So the raw data, in this case, is the user's environment, the physical space. And that data is only generated the moment when the user scans the space. And the ground truth is defined by the user, the object they want to label, and the classes they want to create. And evaluation is also fully determined by the user satisfaction. If they're not satisfied with the model's training, they can provide more data, doing more scans. So formally, we can define in-situ learning as the process of encoding real-time data into a neural network, such that the neural network itself serves as both the knowledge container and the decision-making unit for downstream tasks. So let's see some our vision of intelligent object inventory system through our Magic Leap demo. So on the left, I skipped the part where we select each object and type their names. So basically, the point here is that in a shared office space, we rename objects so that we can clarify the ownership in a shared space, give them meaning. And by doing so, we're actually telling the model which ones are important and what are their labels, so the model can be trained with user's guidance. And on the right side, on a different day, we see that things have been moved, things are disappeared. And we can right away show that what stayed in the room. But if you want to make a list of precisely what are missing, it's a pretty challenging task, because you may have a impression, but with just one click of a button, you travel back in time and you show that what was here and what was the label and what was the orientation. And I want to note that this is not comparing the two reconstruction models, because there will be tons of noises, and this is a neural network doing its job, re-identifying each object to show you that what was here before and what is missing now. And the training takes 10 seconds. So for this academic proof of concept work, there are several limitations. First of all, is the scalability. So it's a trade-off between precision and coverage. The office scene we just showed is 3 meter by 5 meter, and we reconstructed at 4 centimeter precision, and we find that's a good balance for accuracy. And the reconstruction is done in less than 2 minutes on a single RTX 3090. We can also expand to our bigger office with a lower precision, a higher voxel size. But there's always a scalability issue, but we have seen newer methods that can, for example, the ones that Google showed, can make this scale. And for the question and heat map, so it's not really a conversation that we were looking for. It's just a single round. So there are ways that we can take to, for example, adopting the online VLMs to make it multi-round conversation. And right now, we're only limited to 170 common object classes because we adopted offline local segmentation model. All of these are design choices for the consideration of privacy and latency, because we don't want to share anything online. And our system works entirely local and offline and on a backpack computer, if you will, if you like. But the news is, with all of the changing landscape, there are so many offline recent work VLMs that can make the system even stronger by simply swapping these components that we adopted. So the summary of this work is, once again, we propose this multimodal 3D fusion pipeline. And we propose the concept of in-situ learning for user-guided real-time machine learning in AR. And we demonstrated our system in 2 real-world AR applications. And interestingly and importantly, we're open sourcing our code, our sample data, and please feel free to scan the QR code. And I'm ready for questions.
So
Yeah, thank you for your presentation. It was very nice. I'm Yanming from Duke University. So I'm currently also working on using vision language models for scene understanding in AR, which I think is a great tool. So my question is, as you have mentioned that we can use VLMs for a very precise scene understanding, I wonder how do you make the 3D segmentation of the instances like the chair, the Amazon boxes, out of your real-world scene? Yeah.
This one?
Yes.
Yeah, so this one we adopted a local panoptic segmentation method. There are, at the time of this project, there are some open, so this is a closed set detection that used the COCO dataset, 170 classes. The reason we go for this, instead of the same time there were some open language segmentation methods, is for its accuracy. So we could have a long list of million class object classes, but we find that those recent works are not so accurate, even though they support open language segmentation. So what we did here is that for every corresponding view from the scanning of the room, we are doing the same TSDF fusion to integrate the probability of this object class into the separate scene volume, which is dedicated to the object classes. And then we did this, our own custom method of flood fill method. So the flood fill method in 2D is basically the bucket tool in painting, but we did that in 3D so that we trace concatenating voxels of the same class. So that starting from, say, the top left, bottom right, we trace all the pixel voxels of the same class so that we can concatenate them together to know that they belong to the same class. So the shortcoming of this class is that if we have a stack of books all together, because they all belong to the book, they will become one blob of books rather than individual books. So I think that's still a problem that we're solving even with the open language methods, unless you can specifically divide individual books. That remains a problem even with the recent methods.
Yeah, thank you.
Thank you.
I'm sorry, maybe I missed it, but how did you evaluate this? Did you do some sort of user study, or?
Oh, we didn't do. We mainly focused on the technical contribution and the demonstration of the system. There was no user study in this work.
Okay.
Hello, Dieter Schmalstieg from Stuttgart, and I congratulate you on this work, really nice. My question is, you showed this inventorizing, and that has a temporal dimension to it. So you would have to store data for longer time, then index it again and sort of retrieve it or query it. Do you have any idea how that data organization or database might work in the future?
I'm sorry, could you repeat the question part, the last bit?
Do you have any idea or plan or insight into how these future databases of semantic digital twins might look like? Because I think this is very important and I don't know the answer.
Thank you for the question. So in our current implementation, we didn't dive in, is we have this scene manager, which basically acts like a Git thing, a much simplified Git version control that controls different versions of the space that your scans. Then the neural network checks every object that you learned in the past. And basically, literally, we're using a JSON to control which objects appeared in which scan in the history of the space. Very, very naively, I think this method, I haven't thought about, I think the focus here could be some automated method that you can store further, because we're storing the object classes in the neural network. Why don't we just integrate the scene versions, the version of the scans into the neural network as well? So that the self-attention do its own thing, so the model can learn that if these things from two different scans on 2 different days have the same label, then it should reinforce that whether it's orientation or color or shade or lighting changes, it belongs to the same thing. So right now it's pretty naive.
Thank you.
Yeah, thanks.
Okay, then thanks the speaker again.
Thank you. Thank you.
So the next presentation is about XaiR, an XR platform that integrates large language models with the physical world, presented by Sruti, Srinidhi.
You don't need clicker and you don't need audio, right? Great.
Okay. Hey guys, my name is Srinidhi, and I'm from Carnegie Mellon University. And today I'll be presenting XaiR, which is an XR platform that integrates large language models with the physical world. I'd like to thank my co-author Edward Liu and my advisor Anthony Rowe for their help through this project. And today, we have better sensing capabilities, we have better XR displays, we have the emergence of large language models that have generalizable reasoning and have natural language conversations, and so this movie dream is closer to reality. So let's talk about what a cognitive assistant should be. It's something that can understand the world, reason about the world, and then respond to the world. And this requirement seems to lend right into the idea of integrating AI, or LLMs, with XR devices, where XR devices are great at interacting with the world, and LLMs are great at reasoning. Except, this is hard. Firstly, LLMs, even though they're multimodal today, are not great at understanding 3D spaces like our environments. Also, XR headsets are resource constrained. So these heavy, like memory-intensive, compute-intensive, large language models don't really work on XR headsets. And yes, LLMs, or these models now can generate images to some extent, videos, but generating XR content is a little bit of a stretch. So what we have to do is to work around these constraints and try and build a platform that allows us to still integrate LLMs with XR. So the first problem we had to try and solve was that XR headsets cannot run LLMs natively. And so we built this split client-server architecture where we stream all the captured data from headsets to a server, run our LLM on the server, and then send our responses back to the headset. And so this allowed the headset to act as a thin client. Secondly, LLMs struggle to understand users' 3D environment. And so what we did was we captured information about the physical world as image frames and audio. We then took this data, streamed it over to a server, where we had this block that we call the reality encoder, where we process all of this information. We do things like speech to text, frame selection, a lot more, and then we build it into a prompt that can be understood by most multimodal LLMs today. We then take this text plus image prompt and send it to LLMs, get the response, send it back to the headset, and we can get XR content. Except we have so many different LLMs today, and a lot of them are trained for slightly different things. And so we actually added this capability where we can have a bunch of different parallel LLMs. So you can take the same prompt and send it to n different LLMs, whatever your server can handle, and then the response is then curated and sent back to the headset. More specifically for our project, we used GPT-4 vision, and then we used Apple's Ferret model, where GPT-4V is really good at understanding images and providing text responses, while Ferret can give 2D coordinates of specific objects inside your image. And this is specifically useful, you'll see it later in the presentation, but basically it's useful for identifying objects in our scene and creating AR content associated with that. Well, the next thing is we want to be able to produce XR output. And so the first thing we do is we actually, along with images and audio, we also capture the world mesh using the depth sensors on the headset. And then we also keep track of the camera pose at which these data points are captured. So each image that we capture, each audio data we captured is tagged with the camera pose. And then once we pass all this information to the server, get LLM responses, we then pass it through what we call a reality decoder, which basically takes these 2D coordinates we got from Ferret and raycasts it into the mesh from the camera pose at which the image was captured to get the 3D coordinates in space. And with this, we're now able to generate AR overlays. And so on a very high level, our architecture looks something like this. We capture physical world data. We then encode it into a format LLMs today can understand. We send it to multiple parallel LLMs. We then convert the response back into context of the world. And then we're able to provide the user with intelligent XR outputs. Especially for testing, we built an example application on top of this platform, which was an instruction following assistant, which can do two different things. Firstly, it can generate instructions by watching an expert perform a task. And secondly, based off using those instructions, it can help a new user perform the exact same task. I'm going to go through this in a very high level, so for more details, please do look at our paper. So for instruction generation, a super high level, we have an expert. Expert does a task. So in this case, we have them working with a multimeter. We record egocentric video from the headset, and we take segments of this, take image frames from each segment. We caption this, we get a summary. This summary then gets sent to an LLM, and then using the LLM, we generate instructions. The second part is we actually have this assistant use these instructions to help another user do the exact same task. So this is a video of our thing in action. So so here you can see that as they're doing the task, there's text, which is, I'm not sure why this is running weird. Okay, there's text which actually has the instruction the person must perform, and it tells you what the instruction is. It also tells you the current instruction state, so whether the task has been done or not, and what is wrong if they've done it wrong. I just played this, but it also like auto updates, so it checks if you did the task and it moves to the next step on its own. And then, whoa, this showed up real weird. Okay. You also have arrows that are pointing at the relevant objects. So here, for example, it talks about a red cable and the multimeter, and you have arrows that point at the red cable and multimeter. Okay, so how do we evaluate such a system? Firstly, we did a whole bunch of tests to test the system. We did latency numbers, a whole bunch of different evaluations, which are all in the paper. But what I'm going to talk about is a user study that we did, where we basically tried to benchmark this LLM-based assistant and compared that to a human-based expert who's helping you do the exact same tasks. And so if you look at our architecture, we basically built a human backend that takes the exact same prompt that our LLM backend has and provides a response that looks at in the same format as the LLM backend. And so the human gets the exact same information your LLM gets. This is what our human interface looked like. So they got a few different image frames, which is what the LLMs were also provided. And then they have an ability to have text responses as well as draw or annotate on the images to provide 2D coordinates back. The users were asked to perform 2 different types of tasks. One was these basic tasks, which was just taking these colored wooden blocks and arranging them in different configurations. And then they had advanced tasks, which was using a multimeter to measure resistance, and then refilling and turning on a humidifier. So each user did two basic tasks and 2 advanced tasks, where for each type of task, one task had the LLM backend and one had the human backend. And so I'm going to walk through the results really quickly on a high level. So as most people would not be surprised, LLMs are not as good as humans. LLMs are 2-3 years old now, so makes sense. That said, LLMs are not as far from humans as we expected them to be, especially for these tasks. And let me explain why. So yes, your accuracy, yeah, LLMs are worse than humans. But that said, we had only 3 errors out of the 30 different times we ran this for the tests. And we considered an error being either if it got stuck at a step that was already completed for a long time, or if it advanced to the next step, even without the user completing it. But the other interesting thing that we noticed was that the LLM we had to make a significant number of queries to the LLM for each instruction or each step before it detected that it has been completed for the LLM backend. While for the user or for the human backend, it was much less. And this basically tells us that it takes a lot longer for the LLM to recognize what a user's action is. From here, we also see that here we also notice, which was surprising, is that the time it takes for a human to respond to each query is about double than what the LLM takes, which is kind of counterintuitive because most of us complain about how long and how slow LLMs are. But the human actually is much slower. And we notice this basically comes from the fact that it takes you time to type, takes you time to draw, and the LLM can do this much faster. We also had the NASA TLX score, which basically checks the workload that a person experiences when they're working with the 2 systems. And we noticed that the LLM-based assistant had about double the workload than the human assistant. But from talking to our users, most of this seemed to stem from the fact that you needed to make multiple queries to the LLM before it recognized what happened. And so it can lead to frustration because you did a step and you're just waiting for a response. Okay, so from here we came up with a few conclusions. Firstly, if we improve the LLM accuracy, that solves most of our problems, especially given the fact that LLMs are actually faster than human experts at providing responses. If we were to improve the accuracy of LLMs, we would firstly reduce the number of queries we need per instruction. That would then solve the problem of the workload because it would just be a lot faster, and then overall, the task will be completed much faster. Plus, LLMs because they're trained on so much data, they have the added ability to be experts at a lot more different topics than a single human being could be. And so, it's also important to note that LLMs, like if you guys heard the talk this morning, they were not specifically trained to understand the physical world. So we need to collect more egocentric data, we need more physical world data, and if we were able to train the LLMs for these specific tasks, it would help us boost accuracy and improve the overall experience. So yeah, this is XaiR. It's a platform that integrates physical world data with XR devices and multimodal LLMs. And we performed a comparative study on the effectiveness of these multimodal LLMs in supporting physical tasks when compared to human benchmarks. We have an open source implementation, which is on GitHub, or you guys can use the QR code to get to our website. And yeah, thank you, and I'm happy to take questions.
Okay, I think we can have 1 or 2 questions.
Thank Thank you. Very good talk. I have a very straightforward question about how much money do you spend for each iteration of your API query? Because we know for most, especially for spatial applications, they tend to spend a lot of API queries. I'm just curious about your application.
Okay, so that's a good question. I don't have a number off the top of my head, but I can tell you my advisor is not mad at me. So step one. But that said, Ferret we run that locally, so that's free. And then I have only refilled like $50 probably 3 times over the whole development, so not too much is, I think, my answer. Yeah.
Maybe we can have one question in there. Which one?
Thank you for the great talk. I was kind of curious about your user study design when you said that the response time of the model versus the human are kind of, human took it longer, but how exactly are you measuring this, response time? Do you count in, when you make an API query, for example, the, the time going through the network into this time for models? Do you take like the human beings when they're typing and drawing and then, navigating this interface and clicking all the things also into that comparison? And like what exactly is the, comparison made here?
Yeah, that's a great question. So what we did is, like I kind of mentioned, the LLM versus the human is literally like the rest of the network is the exact same, except the actual human entering the response versus an LLM giving a response. So we actually measure it from the time that, we had a couple different numbers. So we have these numbers are from the time the server receives the query gets sent to the server to the time the headset receives the response back. And the way we basically just took how long it takes for each query from that perspective. So that's how we got those numbers.
But you also mentioned that the model actually responded after a lot of queries made.
Yeah. Okay. So that's a good point. So the distinction I think I want to make is that that time number I told you about, like 4 seconds that the LLM takes versus 8 seconds or so that the human takes. That is the time it takes for a single query. But what the other thing I was talking about is that for a LLM to detect that an instruction has been completed and we have to move the next instruction, you have to make multiple queries. So sometimes it doesn't recognize it on the first query, so you have to make it again, multiple times. So there are two different numbers. Per query, the humans take a longer time to respond, but then the humans tend to give you the answers with less number of queries when compared to an LLM.
I see, this makes sense. And yeah, it's still pretty impressive that you built this system and models actually helped. Thank you.
Before going to the next presentation, I just wanted to confirm that if there's the Junxiao Chen for the next presenter here. No? If not, maybe I can have one more question from the audience. Maybe there wasn't a guy raising their hand.
Thank you for your nice talk. So since you were talking about the cognitive assistance, so I seen like you have taken more time to, for instance, human-generated and LLM-generated tasks, the response times. So how you measure the cognitive overload here? So it's take a long time, there is a cognitive burden, or you find?
Wait, sorry, can you repeat that one more time?
So you say there is a much more response time in the LLM-generated instruction. And since it's a cognitive assistance, so since there is a cognitive burden, so how you measure this type of cognitive complexity?
What we used was basically, we used the NASA task load index. We basically talked to people and asked them, how the mental workload was, how challenging they found it, how easy. Basically, we just try to use user studies to evaluate that information. That said, I do want to recognize that this is an initial effort. Like LLMs and XaiR are still not there yet. We all say it's there, but it's not there yet. So this was kind of an initial exploration to understand how this kind of an architecture would work, how effective this would be. And yeah, we basically use user studies to evaluate workload.
Thank you.
Okay, thanks to the speaker again. So the next presentation is the final one in this session. So the title is Encode-Store-Retrieve, Augmenting Human Memory Through Language-Encoded Egocentric Perception, presented by Junxiao.
Hello, hi, I'm Junxiao. You can call me Sean. Today I'll be presenting our work titled Encode-Store-Retrieve, Augmenting Human Memory Through Language-Encoded Egocentric Perception. And thanks to my PhD supervisor, Paula, and my co-worker, John Dolly, that we put this wonderful work. So human memory is incredibly powerful. But we've all experienced moments where we forget important details, such as in the morning, Benko mentioned that, where did I leave my keys, right? So for like, you know, how often you ask yourself, where did I left my keys? What did I do yesterday? Our goal is to create a system that augments human memory using modern technologies, specifically using augmented reality, and also devices such as like smart glasses, wearable computers, and etc. And also, augmented reality doesn't have to be really augment our visuals. Like even augmenting our memories is broadly augmented reality as well. But there's a challenge here. So live logging creates huge amounts of video data, and storing and retrieving specific moments from those videos is really computationally expensive. And in this work, we propose a memory augmentation agent that addresses this challenge by encoding all that's going to be experiences as language and text, and efficiently storing them in a vector database for later retrieval. Let me show you how. So our solution is composed of, so first of all, the idea is to capture egocentric video data, especially video from the user's point of view, and then encode it into a format that allows us to retrieve it quickly and accurately when needed. For example, when user asks, where did I leave my key, and the agent will retrieve from the specific moment and then respond on the table. So here's how it works more specifically. First, the system encodes the video data using a fine-tuned large multimodal model that is specifically fine-tuned on egocentric data that converts visual data into natural language descriptions. And second, the encoded information is stored in the vector database for efficient access. And finally, when the user has a query like, where did I left my keys, the system retrieves the relevant information and generates a detailed response. So that's why we call it the system is Encode-Store-Retrieve. And for the encoding process, more specifically, we've developed a model that fine-tunes the large language vision model, a variant of Lava for egocentric data. And what does this model do? So it captures first-person experiences and focusing on interaction between the user and objects or people in the environment. And this is very important because there are kinds of details that matters most when you're trying to recall memory. Who you were with, what you're doing with, like what objects are involved and so on. And for the fine-tuning process, we created data ourselves using 3,000 egocentric video frames and their corresponding textual descriptions from the Ego40 dataset. This dataset includes detailed descriptions of everyday activities captured from the first-person perspective. And how we fine-tune the model. So we started with the for the fine-tune process. We actually we start with this data set and use a Vicuña 13B and MPT7B for efficient training, and then we do inference using flash attention and a faster transformer techniques. So this is mainly to be used to fine-tune the model and also optimize the model, be used for inference purposes. And later on, after the model is being fine-tuned and trained, we inference them on the frames, and the frames are encoded into text, and then the text is embedded into a vector database. And how we store the text is that we chunk the text into token chunks, and this is like when the paper is made, RAG was not that obvious, but now is like obvious RAG. You basically just chunk the text into text chunks, and then convert them into textual embeddings and then store them in a vector database. And whenever you want to retrieve a specific moment, that you use the query and then to use cosine similarity to retrieve the most relevant chunks in the vector database. And then you output that most relevant chunk with the GPT with your query, and then concatenate them and then use it to feed into a large language model such as GPT-4. So first of all, we evaluate our memory augmentation agent on a large-scale dataset using the QA-Ego40 dataset, which contains egocentric video data and corresponding memory-related questions. The dataset includes 227 hours of videos from 34 different scenarios across 10 universities. So our evaluation metrics includes this kind of includes these three pretty standard natural language processing metrics to evaluate how well the machine-generated text matches human-generated reference text. And our results is pretty promising. The memory augmentation agent significantly outperforms all the traditional models on this dataset. For example, our model achieves a blue score of 8.3, whereas baseline models like the DNC and STM only scored between 3.4 and 5.8. And also the performance improvement is due to the fine-tuning of our egocentric large language model and its ability to really align the video frame features with textual representations. And we also did a user study to evaluate our real-time system. So we conducted a usability study to assess how well the memory augmentation agent perform in the real world and open-ended memory tasks. So in this study, we recruited 12 participants, which includes 7 males and 5 females, with an average age of 26.7 years. And these participants were familiar with AR and VR devices, and the study was carried out using HoloLens 2. And the study had 2 main goals. So the first goal is to compare the agent's performance with human memory in episodic memory tasks. And the second goal is to evaluate how well the agent handling open-ended questions, which require more reasoning and sometimes external knowledge. So here's how it looks like, the 5 tasks. It includes cooking, switching TV channels, reading a book. All the 5 tasks are performed in the actual real house. So the study was like is conducted using. So first of all, the participants are conducted using following the task, and after a week, the participants are required to come back to answer a series of episodic memory questions, such as like where did you place the TV remote, and how many eggs did you cook, and etc. As we follow the forgetting curve of human, and then the agent responses were then compared with the participants' own memory recall. So we found out that we found out that the memory augmentation agent really outperformed the human participants on episodic memory tasks, and the agent's average performance scores was 4.1 out of 5, and compared to the 2.5 out of 5 for human participants. The agent really excels in tasks that require detailed descriptions, especially when identifying like static objects in the environment. For instance, it provided highly accurate description of objects like what the painting looks like, what is the color of the painting, where's the location of the TV remote, etc. However, the agent, we found out that it struggles with dynamic tasks. For example, if it found it difficult to counting moving objects accurately, such as like answering questions like how many eggs did you cook. We also had trouble with tasks that require tracking sequences of actions, such as remembering where an object was placed after being moved. So in addition to episodic memory tasks, participants were also asked the agent 5 open-ended questions, such as what movies would you recommend, or how can I cook an egg better? And the memory augmentation agent's open-ended response received an average score of 3.9 nice amount of 5. So participants really appreciate the detailed and creative suggestions provided by the agent, such as like recommending The Godfather's movie choice or offering detailed cooking instructions, etc. And also, we found out several feedbacks from the participants saying that, like most participants, because we also give them like post-study surveys, and then there's several findings saying that the participants agreed that the memory augmentation capabilities was really valuable, but at the same time they found this a bit privacy concern. But then later on, when I explained to them that all of them are kind of transforming into textuals, and then because it's textuals, then it's very easy to fill out the privacy kind of. For example, faces, names, and etc. Because it's just textual representations, and then then the privacy concerns was kind of elevated by through that kind of textual representing approaches. And also they also give some advices. For example, they really saw that this memory augmentation agent can be really used in other kind of different settings, such as conferences, experiments, and also making the device lightweight and discrete for better social acceptance. So our key takeaways is that the memory augmentation agent provides really a good state-of-the-art solution for episodic memory retrieval, and the participant and then the practical applications in memory scenarios it has a very good user acceptance. And our future direction is that, first of all, we really want to build a high-resolution visual language model for improved performance and long-term studies. Thank you. And also one last thing to note that during this study, we found out that using HoloLens to record things is really the experience is really bad, especially to record really long videos. So we actually made a small device ourselves, which can record like 5 hours of 1080p with 30 frames per second, and it has Wi-Fi and Bluetooth in there. It has 12 MP with 100 FOV. We are open sourcing this hardware. If you're interested in getting this device for your own contextual AI kind of applications, feel free to contact me, and you can get one of them in the very near future, in a month's time or 2 months' time. Thanks.
Is there any question?
Hello, Tobias Höllerer, UC Santa Barbara. Nice work, thank you for the talk. In your episodic memory comparison, between the human and the memory agent, it seems to me that you're comparing two different things. You're comparing a perception and memory effort on the human's part, right, with a detection and classification effort on the agent's part. Do you think that's really all that meaningful? I mean, if you just had waited another week or two, you would have gotten completely different results, right? Because the memory task for the human would have gotten worse, but the detection classification task for the agent is absolutely the same, so you would have gotten the same results there.
Yeah, because human, they actually forget, and the memory the memory agent, the memory augmentation agent doesn't really forget because it's a retrieval task. I fully agree with that. So initially, the study was designed to be more focused on the open-ended questions to really help the users to say, oh, like what movie would you recommend based on the previous experience. So the study was originally designed more on the open-ended questions because to purely evaluate the ability of the memory augmentation agent, the study one already shows the good capability of that. But then we found out that it might be just interesting to show how humans' memory works after a week. So we just designed this study to show a good comparison to get some insights and also to really kind of see how which which tasks human might perform better, which tasks human might not perform better. Yeah, thanks.
Thank you.
Okay, so we can have one more question from the audience.
Hi, Yifei Chang, Carnegie Mellon University. I personally did want to build on Tobias's question. I'm wondering if you can help us understand a bit more about the capabilities of the system. Could you firstly talk a bit more about the evaluation data set you used? I think, in a sense, like how long are the videos that I'm QAing about? Because I think maybe relating to Tobias's point, as a human being, I have a bunch of distractor tasks in between. Is that something that, like, if the model also had, a week of data it had to filter through, then probe back to this time, how well would it do? Like, how specific can I be, and how long can I query for?
That's a very good question. So first of all, this work is about 1 year old, and there's a lot of very interesting progress in my own team's work as well. A year ago, 3-minute, an hour video is considered long videos, but now an hour video is not considered long videos. What I consider long videos is about 100, 200 hours videos. So our team is actually making data sets of over 100, 200 hours long videos. And this is actually what we are pursuing now. We want to have AI to really have a human's memory, human-like memory, to really understand videos that is over 100, 200, even like 1,000 hours long, 1,000 hour long videos. That is why we are making this device to really record like really long videos. Currently, like my answer is that we are not sure. So until we curate the data set ourselves, because there's no data set out there whatsoever. Because for Ego 4D, the longest video is only like an hour. So and as you know, the current state of art vision language models such as Gemini, they can already taking an hour videos without using any of the pipelines. They can just do end-to-end. Although it's like uniform sampling, you sample like 1 frame per second. Although it's 1 frame per second, but then still 1 hour long video is a big problem for the current end-to-end vision language models. So if we really want to show the priority, like the kind of the advantage of this sort of pipeline systems, we really need long videos. So that is what our device is doing, and yeah. Thanks.
Okay, thank you.
So let's thanks to the speaker again. So before closing this session, I apologize that we exceeded the time. But there was a kind of miscommunication in the background. But anyway, so thanks to all the speakers again, and then see you in the reception.